So with this first example, it looks hard. This is a polynomial with coefficients in z, which of course are also rational numbers. And the question is this polynomial, this fifth degree polynomial, irreducible over Q or not? Irreducible over the rationals or not? And what you're almost always hoping for in a problem that looks this hard is that you can use Eisenstein's criterion, and then it's easy. So what you're looking for is whether there's a prime, P, that does not divide the highest degree coefficient, 1 in this case. It does divide all the other coefficients, but its square does not divide the constant term. All right, pretty clearly, P equals 3 works, right? It's irreducible over the rationals by not Einstein, but Eisenstein. We need to give Eisenstein his due compared to Einstein here. With, well, you should say with P equal to what P is, with P equal to 3. Since 3 does not divide 1, the coefficient of the highest power, it does divide, okay, you could just say it does divide all the other coefficients. I'm being explicit here. And its square, 9, does not divide the constant term. What a weird theorem, Eisenstein. How'd you think of that? Well, to tell you the truth, I don't know. I haven't looked it up historically. But if you look at the next theorem, which is a corollary of Eisenstein. So here's Eisenstein's criterion right here, which we just used. Strange little fact. Probably, I'm guessing, Eisenstein was motivated by this corollary. This is called the Pth cyclotomic polynomial, or cyclotomic polynomial. Notice this thing doesn't look like a polynomial, does it? That's a polynomial. Well, they are equal as long as x is not 1. You can double check it's related to finite geometric series. This thing, notice that all of its coefficients are 1. Kind of a special polynomial. Maybe it will be interesting for us to think about this polynomial, but not today. All the coefficients are 1, and the highest power is 1 less than a prime. This corollary says this polynomial is irreducible over Q. How do you prove this corollary? Well, it's Eisenstein's criterion plus a little trick. Instead of showing f of x, or the polynomial capital phi is irreducible directly, you show capital phi of x plus 1 is irreducible. And these coefficients satisfy the condition of Eisenstein's criterion with p equal to the prime that you're thinking about. And if you can show this is irreducible, it also is easy to show that capital phi of x, the cyclotomic polynomial itself, is also irreducible. I'm not going into details. I'm just hinting at what's going on here. Okay, so that kind of problem is actually relatively easy if you're lucky enough that you can apply Eisenstein's. Would I make you unlucky enough that you couldn't? Not for one this complicated with coefficients that big.